We are back at it today with another lesson in Algebra 2. Today we're going to look at inverse operations. So we're going to start this out by relating things that you are already familiar with. So what are some actions that undo or reverse the following? So turning on the TV, what would undo that? Well, that would be turning off the TV. What would undo adding 3? That would be subtracting 3. What would reverse multiplying by 5? Dividing by 5. What undoes subtracting 2? Adding 2. And what undoes squaring a number? Taking the square root of said number. So all of these operations are inverses of each other. So you are familiar with these and you've used them to solve equations. You just probably are not familiar with calling them inverse operations. So let's relate them back to something you are indeed familiar with. If I were to solve the equation 3x plus 4 equals 19, the first thing I would do is subtract 4 because that is the inverse of adding 4. And then I would divide by 3 because that's the inverse of multiplying by 3. And I get my final answer is 5. On the next one, I would start by adding 5 because that's the inverse of subtracting 5. And then I would square root both sides because that is the inverse of squaring a term. And then the last thing I would do is subtract that 4 because that is the inverse of adding 4. And I get that x is 1. On another one, I'm going to subtract 2 because that's the inverse of adding 2. Then I can divide by 5 because that's the inverse of multiplying by 5. And then I need to square root both sides because that's the inverse of squaring a term. And this one is not a perfect square like our previous one was, but the last thing I'm going to do is add 3. And x is 3 plus whatever the square root of 9/5 is. Okay, last one, 2 to the x equals 9. How am I going to solve that? Well, I could find an estimation of what that would be. If I look at 2 to the 1 is 2, 2 squared is 4, 2 to the third is 8, and 2 to the fourth is 16. Okay, 9 is between 8 and 16, so that means my exponent x needs to be between 3 and 4. Okay, how can I find it exactly? Well, what if I graph it? I could graph 2 to the x and y equals 9 and look for where they intersect, and that's at about 3.17, and that does match my estimation between 3 and 4. But is there a way that I could find the exact answer without graphing? Like, how could I solve this algebraic equation? I need an inverse operation for exponentiating. We do have one. It is called a logarithm. So, just like if we had this equation x squared equals 10 and I square root both sides, when this simplifies, you're just left with 10, and then whatever the positive and negative square root of 10 are. If I have 2 to the x equals 9, the inverse operation for that would be taking the log of both sides. This simplifies to just x, and then I can evaluate log base 2 of 9 in my calculator. So what you'll do is hit the math button, scroll down to A where it says log base, and then you can type in log base 2 of 9, and it will give you your answer, which is kind of like what our graph showed, 3.17. So in order to solve these equations, we need to get comfortable going forth between log and exponential form. The base of your log is the same as the base of your exponential, but what you are evaluating changes. For the log, you're evaluating the equals. I apologize for that interruption of music. As I was saying, when you're going back and forth between exponential and log form, the base of the logarithm is the same as the base of your exponential expression. The argument of your logarithm is what you're evaluating. That's your equivalence on your exponential, and your exponent becomes what you're evaluating. So we will have practice going back and forth between these, but just a quick recap and putting this into practice. If I wanted to solve this equation, 10 to the x equals 10,563. What I would do is take the log base 10 of both sides, And remember, my output when I evaluate a log is my exponent. So what this will reduce to is x. And I forgot to take the log of the other side. I apologize. Log base 10 of 10,563. So x is equal to the log base 10 of 10,563. And this is where I use my calculator to evaluate. Now, the nice thing about log base 10 is we call this our common base. So if we don't write a base, we're going to assume it has a base of 10. So you could also rewrite this as just log of 10,563. And you can use this log command next to the 7. That is log base 10. If you have a calculator on your phone built in and it has a log function, that is usually of base 10 as well. So there is our answer. And so what exactly is this telling us? What does log base 10 of 10,563 tell us? Well, it tells us the power to which I have to raise 10 to get 10,563. Okay, we're going to get some practice now going back and forth between log and exponential form and evaluating these, sometimes with a calculator, sometimes without. So here are the two forms going back and forth. On these first 7, we are going to start with a log, rewrite it as an exponential, and then evaluate. So on this first one, log base 10 of 100, well, that tells me that 10 to some power is 100. Well, what exponent when I raise 10 to it gives me 100? That would be 2. 10 squared is 100. On the second one, log base 5 of 5, this means 5 to some power is 5. Well, that's going to be to the first power. Anything to the first power is itself. Log base 6 of 1 over 36, that means 6 to some power is 1 over 36. So I know that this exponent is going to be negative. That is what moves the 6 to the denominator. And then to get 36, I'm going to square it. So that gives us to the negative 2. Log base 2 of 1, that means 2 to the x power equals 1. And to get an equivalence to 1, that means that x is 0. Anything to the 0 power is 1. Log base 2 of 13, that means 2 to the x power equals 13. And if we recall our powers of 2 that we started on the front, we have 2, 4, 8, 16, 32, and so on. 13 is not in here as a perfect power of 2. It's going to be somewhere between 8 and 16, which means it's going to be between 3 and 4, and this is where I would need a calculator to evaluate. So again, math, go down to A, log base 2 of 13 gives us 3.700, and that was matching with my prediction, somewhere between 3 and 4. Okay, on the next one, log base 7 of 35, that means 7 to some power is 35. If I think about my powers of 7, I've got 7, 49. 35 is between those two, so it's not going to be a perfect one, but I know it will be between the first and second, so between 1 and 2. So this is where I will use my calculator again. Math, log base 7 of 35, and I get 1.827, which again matches my estimation. Okay, last one, log base 2 of negative 4, that means 2 to some power is negative 4. Now, if I think about what kind of exponent switched my base from a positive to a negative number, well, I could graph my 2 to the x parent function, and if I recall, one of the features of this parent function is that it's got a horizontal asymptote here. It never crosses the x-axis, and it never becomes negative. So this is going to have no real solution. There are no exponents that switch a positive base into a negative number. Now, what I could do is type this in my calculator to verify this, and hopefully I'll get an error. And what? It gives me an answer, but it has an I here. This I means that this answer is imaginary. So you have an imaginary solution, not a real solution. Okay, our next set here, we are going from exponential to log, and again evaluating with the calculator only when necessary. So on this one, 2 to the x equals 32. That would mean log base 2 of 32 equals x. And if I recall, I wrote these powers up here. This is to the first, second, third, fourth, fifth power. So x is 5. Okay, on the next one, 18 to the x equals 18. This means log base 18 of 18 is equal to x. Well, that means x has to be 1. Anything to the first power is itself. Moving on to 3, this will be log. Remember, if the base is 10, I can just write log of 1 over 100 equals x. If I'm moving to the denominator, that means my exponent is negative. And then because I became 100, that means we squared it. So negative 2. On 4, 3 to the x equals 1. This means log base 3 of 1 is equal to x. So x has to be 0. 3 to the 0 power is what gives me 1. On to 5, log base 2 of 1 over 76 is equal to x. Because this moves to the denominator, I know it's going to be negative, but 76, let's see, I've got 2, 4, 8, 16, 32, 64, 128. Okay, 76 is not a perfect power. It's going to be between 64 and 128. So to figure out what my exponent is, I will have to use the log in my calculator. And that will be log base 2 of 1 over 76. And we get negative, we were correct there, 6.248. Okay, on to 6. 5 to the x power equals 120. So that means log base 5 of 120 equals x. So x is going to be not a whole number again because I've got 5, 25, 125. It's between these two, so x has to be between 2 and 3. And I get about 2.975, which does match my estimation. All right, lastly, 6 to the x equals negative 36. That means log base 6 of negative 36 is equal to x. So what makes 6 to some power equal to negative 36? Well, again, that's going to be no real solution. I don't have an exponent that will change my positive base into a negative value. Okay, I'm running low on time, so I will record the last page in a separate video.